Good morning, distinguished guests, fellow researchers, and ladies and gentlemen. Welcome to my presentation today at International Conference on Biology and Biology Education for Sustainable Development 2026. My name is Caitlin Crisfania Sihombing, representing Universitas Pelita Harapan. Today I am honored to share our team's research titled Comparative Analysis of Brazilian Spinach Growth Using Various Rooftop Hydroponic Methods. This work was a collaborative effort alongside my co-authors from Universitas Pelita Harapan, UPH College, the Chinese University of Hong Kong, and Wageningen University. To put our study into perspective, by the year 2050, the global human population is projected to reach an unprecedented 9.7 billion people. This rapid expansion places intense pressure for our global food system, directly intersecting with the United Nations Sustainable Development Goals, specifically Goals 2 for Zero Hunger and Goal 12 for Responsible Consumption and Production. As arable land diminishes, urban agriculture emerges as a vital soilless solution, utilizing spaces like balconies, terraces, and especially rooftops can dramatically bolster local food security. Therefore, this study evaluates the efficacy of three distinct hydroponic configurations to maximize rooftop agricultural productivity: the nutrient film technique, aerated deep water culture, and the passive kratky system, using Brazilian spinach as our model crop. Let's move on to our experimental methodology. We compare three hydroponic systems against a conventional cultivation control group. Our soil control consisted of plants grown traditionally in polybags filled with humus-rich topsoil mixture. The first hydroponic system evaluated was the nutrient film technique, or NFT. In this setup, a continuous recirculating thin film of 1000 ppm AB mixed nutrient solution was delivered from a reservoir that situated directly beneath 5 inclined PVC channels. Next, we evaluated two reservoir-based configurations. The Kratky system utilized three static vessels filled to the capacity with the same 1000 ppm AB mixed nutrient solutions. True to the Kratky method, this setup featured no active aeration or agitation throughout the growth period, allowing the water level to drop naturally over time. Conversely, our deep water culture, or DWC system, utilized three identical vessels, but with one critical addition: continuous active aeration provided by an aquarium air pump via submerged air stones. For all three hydroponic systems, each vessel or system was populated by 12 explants, each affixed in a rock wool block inside a net pot and suspended using a large styrofoam lid. Now, let's examine our findings, starting with the final morphological growth parameters. All data are presented as the mean plus or minus standard error, and statistical significance was determined using Tukey's HSD test at a p below 0.05 threshold. As you can see from the table, the DWC system demonstrated an overwhelming advantage. It achieved the highest plant height at 22.8 cm and a massive leaf count of 99.3 and a branch count of 14.4, all of which were statistically superior to the other treatments. The continuously submerged root environment in DWC provided a highly stable growing conditions, echoing findings by Chekin et al. And Yang et al. An interesting physiological adaptation occurred in the Kratky system. While its leaf count was lower than DWC, it produced the largest individual leaf area at 10.29 square centimeters. As the water levels dropped, the plants adapted to capture more light by expanding their individual leaf surfaces, sacrificing numeric counts, a classic trade-off behavior described by Whitman and Arsen. Crucially, all hydroponic methods drastically outperformed the soil control across every single parameter. Looking at the final biomass weight, the trend of hydroponic superiority remains clear. Both the Kratky and DWC systems yielded the highest fresh stem and leaf weights, 34.99 grams and 31.96 grams respectively, showing no statistically significant variance between each other, but performing significantly better than the NFT system at 20.02 grams. Why did the NFT system underperform compared to the DWC and Kratky? As highlighted by Alipia et al., standard NFT systems are highly sensitive to external parameter fluctuations, gully lengths, and flow rates, which can induce growth discrepancies. Furthermore, as noted by Sewell et al., flowing nutrients in NFT systems often suffer from localized dissolved oxygen depletion during peak daylight hours on the rooftop, limiting its overall yield compared to a deeply oxygenated DWC system. In conclusion, our study confirms that the growth of Alternatera sisu in a deep water culture configuration is significantly superior to the other evaluated methods, particularly in plant height, leaf count, and branch count. Even though they did not match DWC performance, both the NFT and Kratky methods still vastly increased plant productivity compared to the conventional soil. Ultimately, adopting controlled soilless rooftop systems proved to be a highly effective avenue for boosting total urban agricultural productivity, while successfully overcoming modern land constraints and water scarcity. Thank you very much for your time and attention. I am now open to any questions you may have.